Thank you. Thank you for the brief introduction. This is my first presentation in QIQT, and I am really looking forward to present some of my results that I have obtained in my research career. And again, thank you for that. So I start sharing my screen. Yes. So I hope you all can see my screen, and I'm going to present my talk. So yes. So as I'm going to check the quantum effect of turbulence, quantum effects under turbulences, one need to understand what are the parameters or degree of freedom that can experience the turbulence. And for this thing, I am going to introduce the spatial modes of light. So on this slide, there is something one need to consider is this color bar at the left bottom. So black means there is no light. Color, whether it's red, green, blue, that shows the phase of the laser beam or the light at that point. And the color represents the phase which varies from -5 to +5. And as we go from black to that color, it shows the relative intensity. So we all are familiar with the laser beam, where the phase front of the laser beam is constant throughout and it has a Gaussian intensity profile. If we go to the higher order modes, which there are many class of spatial modes, I have put a few of them. One of them is Gaussian mode, where there is a spiral phase which is the identity of these Gaussian fields. So here your field or the phase of the field varies from 0 to 2i in one circular rotation. Then there is a hole in the center. So there is no light in the center. If you go out of the beam, there is no light. It shows like a donut shape if you record it through camera, and the phase profile is like this. So this corresponds to the degree of freedom, which is called the orbital angular momentum degree of freedom. So here we represent it, this is the +1. We generally denote these higher order modes with two indices. One is L, which is the azimuthal index, and the other one is the radial index. So azimuthal index, here it's +1, here it's -1. The reason is it goes in the opposite direction. So blue to red to green to blue, here it goes in the other direction. Here it happens twice in one rotation. So here the azimuthal index is 2. If we go forward towards the right, we can see additional beams. So those are called as the radial order modes. So for Lagrange Gaussian beams, there are two indices, radial order and azimuthal order. There is one I have mentioned on the extreme right, which are the basal modes. So here the intensity of these beams forms a basal order, basal beams, and in the center there is a hole which represents the orbital angular momentum, or which also called vorticity, because the phase is varying from the center. So here also +1, -1, +2. There is one I have mentioned on the left middle, which is the Hermite Gaussian. So intensity is the insane intensity in the Hermite Gaussian field, and there this is 1, 0. So on the y-axis is 1 because there is one darkness in the center. In the x-axis there is no, 0. So we can associate the index of 1, 0 Here it will be 0, 1, here it's 1, 1. There is a special property of these modes that they are infinite dimensional modes. It's not like polarization here where we have only two bases or two elements in that basis. It's horizontal, vertical, diagonal, anti-diagonal, circular, right circular, polarized line. But it's only two. In this case, we can go from minus infinity or minus infinity to plus infinity like a Gaussian. So because the azimuthal index varies from minus infinity to plus infinity. In Hermite Gaussian, the two indices, one which corresponds to x-axis and y-axis, they go from 0 to infinity. So 0 will represent the Gauss. So for all these family of modes, for Lagrange Gaussian and Hermite Gaussian, the lowest order mode will converge to the Gaussian because all the indices are 0 for this Gaussian mode. So with this brief introduction, here is the outline of my talk. I will introduce the spatial modes a bit more, not just by colors and intensity. I will also explain why they are called higher dimensional states, what are its importance. Then I will briefly explain what are these spatial mode bases. So as we are going to deal with this in terms of quantum mechanical description, I will show you what are the bases, how we can generate them, what are the operations we can perform on them, how we can detect these bases. Because these are the three basic things one required in a quantum optics: how to generate them, how to operate on them, and how to detect them. And then I will come to the main part of the talk, where I will explain to you what are the effects of these, and also I will explain the turbulence, and then I will come to how the turbulence actually affect these modes. So there are two quantum phenomena that I have taken for today. First is the entanglement, which is like whenever you build a source, you have to verify whether it's an entangled or not. So entanglement, you will see how the turbulence affects it, and the other one is the Hong-Ou-Mandel effect, because for any source, indistinguishability is must, and we need to find out how these indistinguishability effects are affected. Can anyone see my screen and me?
We can see you, but not your screen.
No, we cannot see.
Now?
Yeah, it's fine.
And now we can see.
Okay. Because I heard a beep, so I thought to confirm. So this will be the outline of my talk, where I will go through there. So first coming to the bases, I am mostly interested in the orbital angular momentum basis, where the whole field can be represented with this intensity modulating part and the phase part. And this intensity modulation part, as I told earlier, is the azimuthal index, which are integers which varies from minus infinity to infinity, and this intensity part or the mode profile part, it can be Lagrange Gaussian, Gaussian. These are the two most common. So on the bottom, I have mentioned this in a row, where it varies from -3 to 3 for Lagrange Gaussian modes, and on the right, we have these Bessel modes. So the first things comes to our mind, how to generate them. So one of the most easiest thing is by using grating or diffraction. So for this purpose, we use a special accumulator. They are small screens where whatever we put, we put on that screen, and it will modulate the light on the basis of how we modulate them. So here, it's a normal grating superposed with this. You can see it's a pot pattern, which is the combination of the azimuthal phase and the linear grating. And if our Gaussian design is correct, we can see lots of beams in the different diffraction orders. On the right, I have given a particular example, which is the input mode, which is a Gaussian mode. If it falls on this phase function, which is modulated on the special, which is put on a special light modulator. We see a third order OM mode on the first diffraction order. So this is one of the simplest example to generate this. There are of course other methods by using spiral phase plate, by using mode conversion. So this is what I have used. It's one of the most convenient and versatile method because spatial light modulator we can tune it in whatever way we want, whatever mode we want. It's dynamic, it's fast. So this is one of the most easiest one. This and how then? What are the operations we can do? There is one thing that we can do is we can even understand from here whatever mode we have. If we pass through a special light modulator in the transmission mode, we change its value. So if it is 1, if it is 0, we put a 3, whatever we get it's 3. If we have 4, we put a -4, we will get 0. So from here we can understand that this is one of the method that we can also change the mode. So this is one of the operations. Other operation is we will understand when we will generate an antisymmetric state. So these are the two dove prisms. They are the light goes like if it goes on a dove prism like this, it falls on the other surface, it comes here, then it's reflected. So there is one reflecting surface on this dove prism. So if we put two dove prisms and the other one is rotated by an angle phi with respect to the other one, we see that if there is a mode L, it will gain an extra phase of 2L phi. So if we have a symmetric state which is represented by psi plus is for the symmetric, and if we put this combination of two dove prisms rotated by angle phi, we say that at some combination we can actually get antisymmetric state. So if L equal to 1, so it's a first order vortex. If there is a relative angle difference of pi by 4, we go from a symmetric state to an antisymmetric state. So this is one of the operation. This is one of the other operation that we can do on a OM or orbital angular momentum states of light. And the last part, which comes to the detection one, it's by using a single mode fiber. So as we know, it's a single mode fiber, so it can only couple the Gaussian mode. So single mode fiber, whatever its coupled, the efficiency, it can be written as the mode which is input on the single mode fiber, and what is the mode of the single mode fiber. And if we put our input mode, which has this exponential phi L phi, and we have this Gaussian here, so these integration will give us one at non-zero only when the input mode is 0. So this is one of the method to detect them. So to detect, if I need to detect a fourth order vortex or fourth order mode, we will put an SLM. We will change its order to 0, and then we will couple to the single mode fiber. So SLM, a special light modulator, including the single mode fiber, this provides us the ability to measure these higher order modes or orbital angular momentum modes. As we have all these, as we have formulated these basics of this higher order modes, like how we can generate them, how we can manipulate them, how we can detect them. The next thing comes how we can actually harness the higher dimensionality. As we know, polarization can give us qubits, but with higher dimensional states we can go with qtrits, q-quad, and all higher dimensional states. For qubit, we can write a general state as alpha A and B are the two bases. This A and B, and alpha square plus beta square is 1. So this is the pure single photon qubit state. But with these orbital and momentum states, we can write a qtrit, which is combination of these three. In later part of the talk, I will explain what are these and what are the conditions that we can actually take. So with these qtrit states, these conditions lies. And not only this, we can actually write this as a sum of infinite dimension. As we know, these A, B, C for OM states can be alpha 1 will be the OM, beta 2 then gamma 3, similarly we can go with the infinite sum. Accordingly, this pure state, this quantity will change, this orthogonality and orthonormality relation will inherit. And alpha, beta, gamma, these coefficients will be complex numbers. So with all these formulations of introducing a higher dimensional states, we can go from how to generate these in an entangled state. So as in the previous talk, we have heard about the spontaneous parametric down conversion process. Here also, in a brief amount of time, I am going to briefly introduce them. So in SPDC process, what happens is one photon from the laser will disintegrate and give us two photons, which is called a signal and idler. And if these two photons are going in a non-collinear way, like at an angle, we call it non-collinear. If they are going in a collinear region, we call them collinear phase matching condition. And as I told you, it's the phase matching condition which shows that how these angles vary. So these are the momentum direction of the two photons, and this is for the pump. And phase matching governs most of the processes in an SPDC, in the SPDC, nonlinear SPDC process, because energy will always be conserved with those two photons. Here I have represented in like an energy level, but SPDC process doesn't involve any actual energy level of the medium. These are virtual levels, so it just happens instantaneously. So these two photons, signal and idler, they are emitted at the same time. Okay, so as we have seen that phase matching is conserved, so in the phase matching, we can have down converted wavelength. So two wavelengths can be same, or the two wavelengths can be different. So it's governed by the phase matching condition. It depends upon the dispersion property. So as it happens in the nonlinear medium, dispersion plays a very important role in the phase matching condition. The third is as it's a nonlinear medium, bidifferential property of the medium also comes up, and the polarization. So depending upon all these three, here I have shown you two types of phase matching condition, type 1 and type 2. In type 1, if we give a horizontally polarized light, it's a BBO crystal aligned in that particular way that it down converts horizontally polarized photon. What happens is your signal and idler will have same polarization and orthogonal to the pump. In case of type 2, the down converted photons have orthogonal polarization. Is everything okay?
Yes, sir, it's fine.
Yes. Okay. So thank you for the confirmation. So as we have this phase matching condition, let's go ahead and let's understand more about these conservation of momentum. So in the conservation of momentum, if the input pump has the momentum of Kp, if one is Kn, signal is Kn, the other will be Kp minus n. And it will be all the infinite sum. So we can write as K1, if one of the mode is K1, other will be Kp minus K1. If K2, signal is K2, other will be Kp minus K2, and similarly this is the infinite sum. So here Kp is the pump state, we can write in terms of momentum basis, and Kn are the photon states. So that actually correspond to the signal or the idler. And these complete states, they do not factorize. So these are entangled states. Factorize means we cannot separate them in one combination of a signal, one combination of the idler. So by default, these states, the momentum states, they are entangled state. So going ahead, if it's an entangled state, surely we will get orbital angular momentum states of light. So here, if I replace this K with L, which is the orbital angular momentum index, so it's, if the pump is 0, if it is 1, this is minus 1. If this is 2, minus 2, 3 minus 1. So they form an infinite dimensional entangled state. So this is what I have represented in forms of beams. So if a pump beam is Gaussian, signal if it has LS is for the signal mode, Li is for the angular mode, and this will give us some constant value only when Ls is minus Li. So if 1 is 1, other has to be minus 1. So these two indices, Ls and Li, they are anti-correlated. So this is one of the very basic experimental setup that one sees, like a laser from the video crystal, which generates the down conversion, which the down conversion gives us two beams, singular and idler. We separate them using a 50-50 beam splitter. Depending upon if it is type 2, we can use a polarizing beam splitter, because the two output states are orthogonally polarized, and those two states, whatever the signal and idler we get, is typically of spatial light modulator. So that here actually we have allowed
अरे यार थैंक यू भाई, आप तो इधर का बिरयानी खिला रहे हैं हमको, बहुत अच्छा। आप लोग सर कांटेक्ट करेंगे, बात हो गया सर?
अरे सर को हमको कॉल कर रहे हैं।
So correspondingly we will give different these two
ज्वाइन कर रहे हैं,
and we detect and we see the coincidence, because as we go down conductor they will reach to the detector at the same time. So they has to be
ये पहले से हम था, ये बीच में हम
coincidence.
क्या पैसा सिस्टम सब है? कौन सा सिस्टम उस दिन हैंग हो रहा था पहला दिन?
So
आज ये
नहीं ये पहले हम हो रहा था,
spectrum
अब ये हो रहा है। तीनों सिस्टम
नहीं ये हैंग हो रहा था, ये रखा हुआ था, तो हमने ये मंगाया, ये वो खराब हो गया,
what we call as OM.
फिर ये चलते चलते बीच में
So
बंद हो
if
गया,
idler mode, hot
कितनी
mode
कितनी
is
समस्याएं होती हैं जिस
hot
देख रहे हैं।
mode is
उसको काट दिया
signal
हमने।
and
तो फिर
correspondingly
के शायद सर हमको कौन किया, हम भी नहीं
how
उठाए।
much coincidence
सर के सर का हम लास्ट रिजल्ट हमने कहा सर सर का तो हमको कौन उठा, हम पूरा फोन साइलेंट हुआ, हमको सब फील हो रहा है।
zero.
हमको पता नहीं, मैंने साइलेंट चार्ज करा, हमको 4 फोन आया।
So with this one, we actually say that our momentums are conserved. So with all these formulation of entangled states, now I come to the
हमको तो अजीब ही मिला था, हमको
turbulence
नहीं
and
बताया।
scintillation.
हमको अब नींद का सही में प्रॉब्लम
So
है,
as
तो
we are
हम
going
धीरे
to
धीरे
study
अपने
the
आप को
turbulence
एक्सेप्ट
brief
करना
introduction, here I have shown that whatever mode we give, if this is the turbulent medium,
जिस
the output
जो नहीं
will
सोचते हैं
now
बहुत अच्छा गया है,
distorted.
फिर हम रियलाइज
So
करते हैं हम
if this is
कितना बार
our
उठे हैं।
mode that we give to this turbulent
सबसे
medium,
अच्छा होता है
the
बगल में
output
फोन रहता
mode,
है,
depending upon the
फोन
turbulence
फोन पे देखते
strength,
हैं।
how much
दूसरी बार देखते हैं तो
turbulence
5
is
मिनट का
actually
हो गया।
affecting the mode, accordingly we can get how much
सर
scintillated
का फोन आया था, फिर
what
किसी का
we
फोन आया
actually
था, फिर
observe
इनका
on
तो
the
आज
other
कितना
side.
सारा फोन आया था,
So,
फोन मैसेज
there are
इसको
many-
इस बच्चे का फोन
there
आया,
are many
मुझे मेरा फोन खा लिया है।
फिर आप एक एक करके सबको फोन करते
contains the atmospheric turbulence,
अरे मैंने वही कॉल किया था, हमने
and that
कोई
actually
बात
happens
नहीं,
due to the
सभी को दे दो।
and the air
कल भी आप फोन किए थे हमको
is
सच्चे से,
at some
फिर वो
place,
फोन
at
किया।
some
लेकिन
point
आप जो फोन करते हैं व्हाट्सएप मत क्या कीजिए, आप पता नहीं जहाँ से बाहर जाते हैं
concentration of the air,
उससे
somewhere
यहाँ
lower,
पे
this is
बहुत
what
अरे मैं
happens.
नॉर्मल कॉल किया, मेरा फोन
That is,
नॉर्मल को कभी
that
भी
is
रखा
also
नहीं।
flowing, and which leads to this different atmosphere
ना
different
कॉल आता है ना कॉल जाता है।
refractive indices, and that refractive indices actually changes the direction of the mode. So it's multiple flow. You get velocity of the beam that corresponds to the different varying refractive index, and that refractive index
मेरे मतलब
tends
ये
to
एक
different
जियो का ये मान लीजिए मैसेज आ जाता है ना,
propagation. They
सर
change the
फोन के वापस
propagation
रिटर्न
direction
फोन
of
सर
the
नहीं
beam,
उठाया,
and
फिर
finally
मैसेज
what
करते
we
हैं
get
he
is
was trying to contact me,
can be
कैसे
much different from what
ये
we
भाई
get.
अरे मैंने
और
भी
भी
उठाया,
डायरेक्ट
उसने नहीं उठाया।
This is what I mean with the
बदला
turbulence. And there are
फिर
many
उसका एक काम
models
सुन रहे तो
around this.
अभी बीच बीच में बोल रहा है, ये बीच में ये कुछ ज़्यादा ही इंटरप्ट हो रहा है, मतलब
is the
सुनाई दे रहा है, सुनाई दे रहा है।
scintillation.
बोलना पड़ता है।
There you consider the delta
नहीं
point
सुनता।
scintillation.
एक दो बार
So
सुना
here
उसके
I
बाद
have
आगे।
written some of the equations.
टॉप कौन सुनता है?
You will
दिमाग
find minimum
दूसरी चीज पे रहता है दिमाग।
So
दिमाग
this
रहता है
CL
कि
square
इस तरह से प्रॉब्लम ना हो जाए, किसी तरह का गेम ना हो जाए।
YouTube अभी वो चले गया, मुझे YouTube पे देखना पड़ रहा है।
because this is one of the part which is most necessary. The reason is because we are trying to simulate that the actual turbulence what we can see in the atmosphere. Like even you see clouds, they are not completely random. They are not random like dots or we generate random numbers. They are random in terms of like they have a structure.
क्योंकि उसने वो लैब में देखा मैंने मैंने पहले
Have
3 लोगों का नाम
has
बोला, फिर
something
इनकी
called
याद है, धीरेन्द्र याद है,
structure
फिर धीरेन्द्र
constant.
नाम बोल दिया।
And there are some
फिर
weird
मैं सोच रहा था कि किसका
power
नाम
law
लूं,
is
मुझे
that -11/3 -2. And for more information,
देखा
one can actually
भाई
go
बारिश में
through
ट्रेन रुक गया
these
भाई
suggestions
मेरे
to
हिसाब
random
से कि
area.
हम आपको बोल
It's
दिए
a
हैं
very
कि
good
विल
reference
टुमारो
to study
तो
this
हमें तुम
university.
हम डर के कौन मेरा
Going
मैसेज
forward,
किया, कौन मेरा मैसेज
with more of the
समझे नहीं आ रहा था,
structure
हमको मैसेज कर दिया।
So we have,
पर
so
हम नहीं किए
these
थे
are the
ना।
3 parameters, 4 parameters.
हम पता नहीं क्या करते हैं, रात में सीधे उठ के फिर 9 बजे
So
सुन पूरा
this
देख
is
रहे हैं।
something which is necessary
third round.
because how much phase
third round.
it depends upon Z.
दो round में तो
So
classical
how
जीता,
much
third round
phase
classical
is required once if the beam passes
तो
through
क्या होगा
the
बताइए
first
मैच कैसे होगा
more medium,
किसका?
more accumulation of phase. Then there is this structure
Classical.
function, fluid parameter, turbulence system. So finally this turbulence strength, what we call W, it depends, it is the ratio of W0 and R0. W0 is the input beam rate and R0 is the feed parameter. And here your wavelength is lambda, C square is the reflected index structure function. So we have this, how we can generate this turbulence. But there are 2 models that one can expect. Because as you have more turbulence, you can have, you need more experimental resources and more computational resources to simulate. So what one can do is, there are 2 approximations people can work on. First is the single phase approximation,
लेकिन
another one
टूर्नामेंट
is
फिक्स
multiple
ऑफ कोर्स वो
phase.
कराएंगे जैसे इसका नाम आप
So in the first one, in the single
लेकिन भाई मुझे गेम सब भी खेला है वैसे खतरनाक खतरनाक गेम
space
सब
the
मजा
turbulence, you take
चार
an
लोग
equivalent
चार लोग
phase
थे
free screen,
और
just one,
चारों लोग
which gives you the
मतलब
same
आपस में खेले थे
output.
12 लोग
Because in lab you can do with the SLM, and we cannot have infinite SLM. So what you can do is, you can take this approach where whatever turbulence you want, you compress them into one phase screen
रेटिंग कहाँ
and
बढ़ेगा यार
study
एक्सेल
them.
पे
The
प्लेटफॉर्म
other
में भी खेले और
approach
उसको
of
2
the
पॉइंट
more
मिलता था
general
हाई
one is a
पॉइंट
multiple phase screen.
हाई एक बार ड्रॉ करता था 4 पॉइंट
Like
लॉस
if this is an entanglement system, where you can put multiple phase screens on the 2 on the path, and then in the end with the quantum state tomography
वो
or other
रेटिंग
techniques
डिफरेंस इतना
to
कम होता है ना
measure
10-15
how
मिनट
much
कब आया
entanglement is left on that.
प्लस माइनस 15 देखिए उसमें सब आ जाता है
So
बस टॉप
these are
तक
the 2
इन या दो जो है वो होता है मैंने
And
साथ
here
में टैक्स
under
का
actually one of the
बहुत
phase
खेलने
screen,
लगा तो
here you can see that it's more, it's not like completely random, but they look like clouds. Okay? In this case, what you can observe is the beam will
Indian
not
tournament का ये
get
तो पहुंच
completely
गया
distorted.
जैसे सिद्धिंग में कैसा नहीं समझता
Depending upon the turbulence, you will have the effect of turbulence strength.
उस पैक वाले लोग नहीं खेलना चाहते हैं 25 और 26 वाले प्लेयर्स
So
कार्सन ड्रॉ किया था
these are
तो क्या
delta
होगा
correlated functions. So between there
जितना वो
is a
4 में
correlation
जीत के नहीं उसको गेन
between
हुआ
points
उतना
of
ही मैं चल रहा करके उसका उतना कम हो गया
So
उसका फिक्स हो जाएंगे
they are not going
सारा
to,
29 का चलना चलेगा
anything else, like the total input intensity will be the total output intensity.
ये बीच में हैंग हो गया था, फिर भी हैंग बीच यूट्यूब चल रहा है उसके बीच में बंद हो गया।
लोड को नहीं उठा पाया सोचे पिछले साल ये इन लोगों को 16 जीबी का रैम दिया गया है तब नहीं हो रहा 4 जीबी के रैम में पिछले साल पूरा खेल
Very
किया
far one. Not
जब
very
पता
small.
चला उसने 4 जीबी का रैम इतना तकलीफ में हम चले गए थे हम लोग के साथ इतना गलत किया जा रहा है इतना काम हो रहा
Now
है
I come to the main part of the talk. Here I am going to explain some of the results that I have obtained. Especially because I have
वो लकी था कि
formulated
जैसे वो हैंग हुआ ये सब
what are the things that we require to perform this.
देखिए सब थोड़ा बहुत ट्रबल आते रहते हैं
This is what this is how we started.
आप अपना
First we
देखा
set
कहाँ
up
when
this
how दिन में
SPDC source.
वो ये
So
जाके
if
वहाँ
we
पे
put
पेन
the camera here and if we take
अपने से नहीं हो पाया
this
एक्सपीरियंस दूसरे लोगों से
we are going
एक्सपीरियंस
to
करें
see that we go from collinear region to non-collinear region. And every region has its own disadvantages and advantages. So, working in a bit non-collinear is okay, but working at highly non-collinear is again not okay. So, this is the reason I choose where these two beings, as you know, that they will be generated at 180 degree. So one photon, if the signal is here, idler will be diametrically opposite. So these 2 points I chose. So and then I put on the SLM. This is how we do the quantum state tomography. So on these two spatial light modulators, we scanned through all the modes, like these are the +1, -1, superposition of +1, -1. So it's, you can say as if these correspond to horizontal, vertical, this corresponds to diagonal and anti-diagonal, this corresponds to left circular and right circular. So I'm taking an analogy with the polarization. So this is how we scan through all 6 of the combinations to perform the quantum state tomography. So whatever the states output we are getting, we are going to do that. So once we get the tomography, we calculated the density matrix. So when we are not doing any turbulence setup, or when we are not introducing any turbulence on any of the SLM, what we get is the pure state. So the value we get is for one, like you can see, if one of them is -1, other is +1, I get a peak. So all the center 4 points are giving us the peak and all others are giving us the 0. So this would be the ideal density matrix one can observe if there is no turbulence there. With turbulence, what is going to happen? It's like this. So OM mode is getting scintillated. So what you are getting at the end is the loss of entanglement. So how do we actually determine how the state evolve in a turbulence? So we set up the complete experimental setup. Here you can see one of the most common entanglement setup one can set with the higher order modes. So we have the BBO crystal, we have one of the filter. So this filter will remove the pump because we want to detect only the single idler. With this lens and this lens, we image the BBO crystal on the spatial light modulator. And with this lens and this fiber coupling lens, we image the whatever the modes it's coming from the SLM, we couple to the single mode fiber. So this SLM and this single mode fiber act as the detection system. So all these are in the image plane configuration. BBO is imaged onto the SLM and SLM is imaged onto the fiber tip. These are some of the lenses combination I used. So what state we used? So as we have this we had the freedom to use the higher dimensional states. Why to go with qubit? Let's go something big. So what we use is a qtrit. So we took 3 states with these combinations and we put turbulence on only on one of the SLM, because with two, we of course you can use both of them, but for this study we put only on one of them and we wanted to see how the entanglement varies. Then we need to find out what should be the measure of entanglement, and we used, for the measure of entanglement, we use the negativity instead of concurrence. So for qubits we use negativity, and we use the qubit state something like this. So the 3 modes we need here, it's we took L equal to 1 0 -1 or -2 0 2 -3 0 3. This is the way we took the qubit state. So we wanted to be symmetric bit from the L equal to 0, and we took large number of as it's a qubit, then these many number of measurements you need to perform to get one tomograph. So this is the for full state tomography. To reduce the number of measurements, we took only the reduced tomography measurements, and which were 81. So this is one of the reason that people go with reduced tomography measurement, because the number of measurements are reduced. So here is the plot of how the negativity varies with the turbulence strength. So this is one of the density matrix where there is no turbulence. So these are the ideal modes that you can have for qubit. And as you are increasing the turbulence, what will happen is the modes scatters to the or the tomography, in the tomography measurements, you get other peaks. And when you take the negativity, they varies a trend. They decrease when you increase the turbulence. But this is not the main result. The main result actually comes here. If you have low turbulence strength, lower order modes are preferable because they have less turbulence effect due when you increase the turbulence. But as you go higher turbulence strength, the higher order modes are going to give you better entanglement. This is one of the results that was very interesting in terms of, like, one can say that okay, higher order modes are more affected, but it's not in this case. So if I will show you a condition where this will be very useful. So going forward to the another topic, another effect which is called as the Hong-Ou-Mandel interference, and this is what I have not introduced, so I'm going to do briefly. So when those two photons, Signal and Adler, they reaches the beam splitter, there are four possibilities can happen. Either both of them go in single path, or they transmit or reflect. So these are the four combinations available. According to Hong-Ou-Mandel, what they proposed, like they did it for some other purpose, but the conclusion was that if those two photons are really indistinguishable, in that case, they will bunch up. So if they are twin photons or they are SPDC photons generated at the same time, both the photons will actually follow this trend and not this, because their combinations are there is a negative sign though, so they get destructive interference. And if these two happens, what will happen is you will not get any coincidence, because as those two photons are not going to the two detectors, there is no coincidence. And we wanted to see the effect of turbulence on this case. And Hong-Ou-Mandel, it's very necessary because you need in entanglement swapping, you need to generate higher these antisymmetric states and many other applications of Hong-Ou-Mandel interference. So a bit of theory, what we did is we took the turbulence operator as this, we introduce as one of the photon is not, we have taken two cases where one photon, only the photon A is affecting the turbulence and not the other one. So in this case, your B, so this is the beam splitter operation where this mode can is translated to this. And when we expand everything and if we measure the coincidences, we see that it comes down to zero because you are not going to measure any coincidences. So this shows, and the symmetry actually, the answer lies in the symmetry, where if your one photon is affected by the turbulence, you are not going to see any dip in the coincidence. You are not going to see any difference in the visibility. Your visibility will always be perfect. Means your Hong-Ou-Mandel result will always be perfect. So if we do the complete theory, this is what we get. Even if we increase the turbulence strength, our visibilities are not going to change. So this is the symmetric input, this is the antisymmetric input. And if we are introducing both the turbulences, both the beams, so we have this turbulence parameter A and this turbulence affecting the B photon. So if we introduce the turbulences to both of them, do a bit of theory, what we see, the coincidences, it's a combination of this and this. So here, actually these two parameters, A11 and A12, they are the modes which actually converts one to the other. This 1, 2 and here 1, 2. So this says that whether your turbulence is affecting how much, or your mode L equal to 1 is changing to other mode or coming back. So if those type of things happen, finally, if we do the whole theory, you get this type of parameter, and you can see that this thing 1 minus f2 inverse, and f2 is a big parameter, and then W0 by WP is alpha. You have this turbulence strength, another parameter. So this is what the experimental setup we set up, where we have the palm. Then we are changing from symmetric to anti-symmetric state using these two Dove prisms. So if we rotate it by pi by 4 or 945 degree, we convert from symmetric to anti-symmetric. One of the SLM, either this or this, is introducing the turbulence to the photon, and then we are measuring in the end with another two SLMs. With all these, so here I come to the first part of these results, where if there is no turbulence or the turbulence strength is 0, and if we take whatever number of combination of turbulences, uh, the visibility is always more around 90%. So this, whatever we are observing here, these are the background or accidental coincidence. But as we have increased this turbulence strength with the 0.4, we find that when both the photons are passing through the turbulence, this lower value always remains the same, but the upper, the number of photons coupled to the fiber, they are different. So here, from here itself, we can see the visibility is going to change. But with the if there is a single-sided turbulence or only one photon is affected, then there is no change in the visibility. And this is for the anti-symmetric state. The results are same. So in anti-symmetric state, what will happen is, instead of bunching up, they are anti-bunched up from the beam splitter. So they will give coincidences. So with double-sided turbulence and single-sided turbulence, this is how your Hong-Ou-Mandel dip will look like. So we took in such a fashion that we get that peak or the dip, and we also get some light on the, so that which form as a basis for how many photons are coming up. Here also you can see that it's not symmetric, but you get a dip. But first thing, we need to see how many photons are actually reaching to the detector. So in this case, these are the average number of photons that is reaching to the detector in 25 seconds. And we can see that as we increase the turbulence strength with this zeta, different parameter than earlier, we can see that if the turbulences are increasing, the number of photons reaching to the detector are less. And if it's a symmetric state or single-sided, if there is a single-sided turbulence, relatively more number of photons are reaching to the detector than the double-sided turbulence. So double-sided means more photons are getting scattered to different modes, and if they are scattered to different modes, they are not going to couple to the fiber. So this is how the visibilities look. So the green curve here is actually the theoretically obtained curve, and so you can see that it matches very well with the symmetric state, because so symmetric, if there are no losses, you should get a visibility of 1, but due to experimental resources and something, you get less, but which were constant throughout the turbulence strength. So this is for the symmetric state, and similarly for the anti-symmetric states, the results were varying well. So now coming to this point of like the first one, where we introduced the turbulence to only one of the medium, and we got like this is for the Hong-Ou-Mandel case. So where if your one photon is affected from the turbulence, and then maybe you can see that one is passing through the turbulence, another is the optical fiber. So as you can have less loss from the optical fiber, what can happen is, still one photon is affected through the turbulence, you are not going to see any effect on the visibility. So this is one of those applications where this type of a study will be useful. Similarly, if we see the variation of entanglement with turbulence, that also we have simulated this case where only one photon is affected by the turbulence, not the other one. So with these two results, I now finally come to the conclusion of my talk, where we see with an increase in the turbulence, we see the entanglement is reduces. And that entanglement we see for the qtrit, surely qubit will also happen. But with qtrit, you can see that at higher turbulences, your higher order mode should be preferred. And lower order modes are preferred at lower turbulence. Similarly, in the Hong-Ou-Mandel case, if there is only one of the photon is affected by the turbulence, there is there will be no relatively change in the visibility of the Hong-Ou-Mandel dip. It's only how many photons are reaching the detector, they will be reduced. As I was introduced, I have joined Physical Research Laboratory recently. Here we have access to 200-meter free space atmospheric channel. So some of these results we are going to test in the field, maybe in the next season, maybe rain is coming soon. So this is what my plan is for the for future. So with these two results and this brief summary and the outlook, I thank everyone for the attention and I am open to questions. Okay. I have, is everything okay? Are you audible? Okay. So I have found two questions on the chat. Is there turbulence directly or indirectly related to key generation? Yes, turbulence affects the key generation, not the key generation, but the key detection. So we have a very recent paper published in Journal of Optics where you can see that not the turbulence, but the atmospheric parameter, you can actually relate it to how much key you can get. So more turbulence, less key rate you can get. And how does turbulence makes easier in quantum communication? Certainly, it's not going to make the life easier. More turbulence, life tough. Okay, because especially with these higher dimensional states, if you go with polarization, you're as the atmosphere doesn't introduce that much polarization effect, polarization degree of freedom is preferred. And if you want to see the turbulence, there are some modes which are more preferred and which are more preferred than these OM modes. Now some simulations are going on to find out that in higher turbulences which type of modes are more preferred and you get less effect of turbulence in the end, or how to correct them. So yeah, anything more, please. Even if you come up with any questions later on, you can email me. I will be happy to answer.
Hello, I have a question. Can you go back to your conclusion?
Yes.
Yeah, see, this your conclusion is that in this home interference is not affected when one of the two entangled photon goes through turbulence.
Yes.
In two photon interference, generally it is known that even if they are incoherent, the two photon interference doesn't get affected. So this probably is not surprising, no? That
The
difference of one photon is not affecting this home interference.
one photon will not affect, because then this is one of the we also have the same question, and this is why we actually perform the whole detailed calculation you can find in, and there it's like it also lies in the symmetry and also in this the basic calculation that I had showed in forms of these operator calculation. So if it only comes down to the visibility, if you are not interested in the number of photons reaching to the detector, this single-sided turbulence is going to give you will give you the perfect visibility but less amount of.
Okay.
So double-sided turbulence means more noise and also your visibility is changing.
Okay. So other question I have is that see, I believe this orbital angular momentum experiments, they also work even if you go down at the level of single photons,
Yes.
right? So, but is there a theoretical understanding of how an angular momentum, orbital angular momentum state would be for a single photon? Because
Okay.
for
Okay. So this is something I try to explain with these. Okay. Maybe here, because your photon, when you are getting a signal and idler,
hmm,
what will happen is there will be momentum conservations. So if one photon is getting -1, other has to be +1.
hmm,
And if you if you want to get the mode structure, it's even in the photon region and also in the mode structure region. Because if we are using a spatial light modulator to measure them, this shows that your wave packet has the information about the space or the spatial degree of freedom, and also the photon. Your photon doesn't lie in one point. Like, if your beam is a donut shaped, you cannot say that your photon is just one. It can be anywhere. So this is how, when you do the collapse of the state using the spatial light modulator and select using the fiber, everything goes to Gaussian.
okay, thank you.
Thank you. There is another question in the chat. Is there meaning of free space is vacuum? Yes, free space is not vacuum. You can say it's the lab environment where you do not see any atmospheric effect. It's ideal condition, no airflow, no turbulence, not much people are walking, something like that. Temperature is constant throughout the lab, dust is less. So free space, something like that. And if you are talking about the free space channel that I discussed here in my outlook, that free space is the atmospheric channel. So it's like one building to the other, communication similar to that.
So essentially, it means without waveguides.
Yes, without waveguides.
Without waveguides. So if there are any more questions, uh, you can put them in the chat box, or you can send Dr. Prabhakar an email. Okay, there's some comment
There is another
there.
chat. There is another. So the increasing turbulence also leads to lowering the speed in BBM 92 protocol. That is all. Yes. So if you are going to do with a spatial mode of flight, certainly, as you know, turbulence affect the modes and they scatter to other modes. So certainly your key rate will be lower. But yes, in that case, you can. We have not seen this with how much extent. This is what my plan for the next round of experiments from the channel, because I recently joined and still things are going on. So maybe by next year, I will be able to present something in this regard. Okay, I have stopped sharing my screen.
Yeah.
Thank you. And I thank everyone for listening.
Yeah. Thank you for your wonderful lecture, which was well timed, very clear, and you went on very slowly so that we can gather it.
Thank you.
So if there are no more questions, we can close the session, but we still have about 4 minutes to close. Okay, looks like there are no more questions. So in case there are any more questions you come up with, you can send Dr. Prabhakar an email. I believe he will He'll be happy to answer them.
Sure.
So we can all meet again in the afternoon session, which starts at 3 o'clock for the two lectures of one by Professor Philip Walter and one by Dr. Gautam Shramanto. So we can end the session now. Thank you.
5 minutes in fire, gypsum board turns into ashes. But Hilux board can even take a hammering. True false ceilings only from
Incidents.
5 minutes in fire, gypsum board.
These modes, and they are infinite dimensional modes. It's not like polarization where we have only two bases or two
Angular momentum, orbital angular momentum state would